In the heart of industry, temperatures exceed 3,000 degrees Fahrenheit.
This is not just a factory. It is a fortress of fire and physics.
Here, the discarded remnants of modern life, old cars and appliances, are reborn. Transformed into the high-strength arteries of global infrastructure.
A process demanding slightly more power than a small city.
Where brute force meets microscopic precision. We are tracking the creation of the seamless steel pipe. The journey begins not with mining, but with harvesting the old. The scrapyard is a chaotic landscape of sorted metals. Massive electromagnets lift tons of ferrous material in a single hoist. Before melting, larger debris must be shredded into uniform pieces. Spinning hammers pulverize steel in seconds.
Non-ferrous metals like aluminum and copper must be separated.
The sorted steel, known as shred, is loaded into a charge bucket. Operators follow a strict recipe to ensure the final chemical composition. This single bucket holds over 100 tons of potential energy. The charge is moved into the melt shop, the heart of the operation. Here, solid metal will vanish into liquid. The bottom of the bucket opens, releasing the scrap with a thunderous crash. The furnace roof swings back into place to contain the inferno. 3 graphite electrodes, each the size of a tree trunk, descend. Contact. A massive electrical short circuit creates the arc. Millions of watts surge through the graphite, turning electricity into pure heat. Supersonic oxygen lances are inserted to accelerate melting and remove impurities. Impurities float to the top, forming a protective layer of slag. Operators take a sample to check the carbon content. Once the chemistry is closed, the furnace tilts for tapping.
The tap hole opens, and liquid steel streams into a ladle below.
The furnace tilts back quickly to keep the slag inside. The ladle, now a bucket of liquid sun, moves to the refining station. The melting is done, but the engineering is just beginning. At the ladle furnace, the steel is fine-tuned like a chemical solution. Argon gas is bubbled from the bottom to stir the mixture.
Precise amounts of manganese, silicon, and vanadium are added.
Lime is added to pull sulfur out of the steel. Aluminum wire is fed deep into the bath to kill any remaining oxygen.
A final sample confirms the steel is ready for casting.
For high-pressure pipes, hydrogen must be remolded in a vacuum tank. The vacuum rips gas molecules out of the liquid metal.
The liquid metal is now chemically perfect. It's time to solidify.
The continuous caster transforms liquid batches into an endless solid strand. Steel flows into the tundish, a bathtub-sized reservoir that buffers the flow. The tundish distributes steel into multiple molds simultaneously. Inside the water-cooled copper mold, the outer shell freezes instantly. The mold vibrates to prevent the steel from sticking to the copper.
A glowing red strand emerges from the bottom, liquid inside, but solid outside.
High-pressure water sprays harden the core as it descends.
The vertical strand is gently bent into a horizontal position. Straighteners pull the strand onto the runout table. Oxygen torches clamp onto the moving steel, cutting it into billets. The result is a solid round billet, the raw stock for pipe making. Each billet is stamped with a heat number for traceability.
Billets are stacked and stored, awaiting the rolling mill.
To shape the steel, it must be softened again. The walking beam furnace slowly marches the billets through zones of increasing heat. They must reach a uniform 1,250 degrees Celsius throughout. A glowing billet exits, soft enough to mold. High-pressure water blasts off the oxide scale formed during heating. A pneumatic punch marks the exact center of the face. Now begins the most violent step in pipe making, rotary piercing. Two barrel-shaped rolls spin the billet and drive it forward. The pressure opens a crack in the center of the solid steel.
A water-cooled alloy point is thrust into that center opening.
In seconds, a solid log becomes a thick-walled hollow shell. To thin the walls, a long mandrel bar is inserted. The pipe and bar pass through a series of rollers, squeezing the steel against the bar. The pipe stretches to 3 times its original length. The mandrel bar is extracted, leaving the hollow pipe behind.
The pipe has cooled slightly, so it passes through induction coils.
The stretch reducing mill determines the final outer diameter. It creates the exact size required by the customer. The pipes roll onto a massive walking beam cooling bed.
Constant rotation prevents them from warping as they cool.
For high-strength applications, the steel's crystal structure must be altered. The pipes are reheated to the austenitizing temperature.
Sudden cooling freezes the microstructure into hard martensite.
Steam explodes as the steel temperature drops 800 degrees in seconds.
The steel is now hard, but brittle like glass.
Tempering reheats it gently to restore flexibility.
The result is quenched and tempered steel, tough and unbreakable.
A ring is cut from the pipe end for destructive testing.
The Charpy V-notch test measures your impact toughness. Tensile machines pull the steel apart to measure yield strength. Heat treatment can warp the pipe slightly, so it enters the rotary straightener. It emerges perfectly straight within a fraction of a millimeter.
The rough ends are chamfered for inspection.
Inspectors look for surface defects.
Laser calipers verify the wall thickness and diameter. But the most important tests happen below the surface. Non-destructive testing ensures no hidden cracks exist. The pipe is washed to ensure sensors make good contact. The automated line feeds pipes one by one.
Ultrasonic probes spiral around the pipe, sending sound waves into the steel.
Any internal flaw reflects the sound wave back to the sensor. Magnetic flux leakage detects surface imperfections. Operators monitor complex signals in real time. If a defect is found, paint guns automatically mark the spot. Every single pipe must survive the hydrostatic pressure test. Water is pumped in until pressure exceeds 10,000 psi. It holds the pressure for 10 seconds to prove integrity.
The pressure is released, and the pipe is certified.
A drift mandrel is pushed through to ensure the inner diameter is clear. Human eyes give the final approval. CNC lathes cut precision threads onto the pipe ends.
A coupling is screwed onto one end with exact torque. Plastic caps protect the threads during transport. A layer of varnish prevents rust during storage.
Specs, size, and heat number are stenciled in white paint.
The final length and weight are recorded for the customer. Pipes are strapped into hexagonal bundles. Gantry cranes move the bundles to the shipping yard. Rail cars are loaded for transport across the continent. from a rusted car chassis to a high-pressure energy conduit.
We witnessed the violence of the electric arc.
And the microscopic precision of the rolling mill.
A testament to the engineers and workers who tame the heat.
These pipes will now carry the resources that power our world.
This is the modern alchemy of steel.